In this section of notes, we'll be looking at the effect of electric current on the human body, and we'll start out with a couple of cartoons that illustrate what we're talking about. In our first frame, we have a character saying, "You're never going to believe what I just caught Skull doing in the kitchen. He was fishing a piece of toast out of the toaster with a metal fork while it was still plugged in. Then he tried going at it with a spoon. I had to hide all the silverware." And of course, we know that silverware is a conductor. So if you were to touch the hot element of a toaster, you'd be providing a path to ground. And that would allow excess charge to flow through you to the ground, which would be very dangerous. Then we hear a terrible noise, a zerk, which must be some kind of spark. And then she says, "I must have missed a butter knife. It's like living with a baboon." Okay, so we know that that's very dangerous. And now we're going to look at a cartoon that provides some math behind the situation. Skull has been acting really weird since his accident. Well, he got zapped with a lot of volts from that toaster. Now we finally meet the character Skull here. That's Skull. And Skull says, actually, it was the amperage or the electrical current driven by the voltage of the toaster, 120 volts, and the resistance of the path through my body. And this is exactly the right language that this character is using. The voltage drives the current or pushes the electrons through the body. If the resistance of my body was around 100,000 ohms, and that is correct, then the current produced by a 120 volt toaster would be 1.2 milliamps. So he's using current, taking Ohm's law and rewriting it, taking the voltage, 120 volts, divided by 100,000 ohms to get the 1.2 milliamps, which would be 0.0012 amps. Barely enough to make a tingle. So this is a very small amount of current, relatively safe. But I was barefoot and wrought with perspiration. My resistance should have been 1,000 ohms. Now this is why water and electricity is so dangerous. 100,000 ohms is 100 times more than 1,000 ohms. And reducing our resistance by that much would increase the current by a factor of 100. 120 milliamps is 0.12 amps, and that's pretty high. That would actually cause muscle convulsions. And then the last frame is, like I said, weird. So presumably this character got smarter after being electrocuted, which I'm not sure is an accurate portrayal, but I liked the math in this example. So now let's summarize what we've learned here. What does voltage do? Voltage pushes current through the circuit. And it provides energy to the charges. It provides a sort of potential energy. So when we think about like 120 volts, that means 120 joules of energy per coulomb of charge. Here we've got a little chart to show us what can happen with different amounts of current. With 1 milliamp, you can feel that. Now, back in this last problem, we had 0.0012 amps or 1.2 milliamps. You would not feel much from that. But 5 milliamps is painful. 15 milliamps can cause a loss of muscle control. And I think the Van de Graaff is somewhere between those two. And then as little as 70 milliamps can be fatal if it goes through the heart for more than 1 second. Now, all of this depends on different conditions. The body can have a range of as much as 500,000 ohms of resistance, all the way down to 100 ohms of resistance if your skin is soaked in salt water. So again, it really matters. Water and moisture really matters, because water that is not distilled, water that's not pure, is a pretty good conductor. And so that, again, really lowers our resistance. If you were to touch a 120 volt wall outlet, there would be a 120 volt potential difference between you and the ground. And since 75% of our bodies are made of water, the interior of the body is a pretty good conductor. And the real question is, where will that charge pass? If it passes through your hand or your foot, it's probably no big deal. But when the charge passes through your brain or your heart, that is bad. The electric shock, what it really does to your body tissues is it overheats them. When you think about current, if you have a lot of current, like 1 amp, 1 amp of current is going to bring a lot of energy through the body. And that energy has nowhere to go, and it will be dissipated as heat. So it will essentially cook the tissues. It can also disrupt nervous functions and nerve messages. So that's extremely dangerous. So let's look at an example here. Calculate the current produced by a 12-volt car battery when you touch the electrodes with your dry hands. Okay, do not do this. You can get quite a shock from a car battery. So the voltage here is 12 volts, and the resistance is 100,000 ohms. And we'd like to know the current. So we know that V equals IR, and if I rearrange that, current equals voltage divided by resistance. So that would be 12 volts divided by 100,000 ohms. And being lazy here and getting out my calculator, 12 divided by 100,000 is 1.2 times 10 to the negative fourth, or 0.00012 amps. Now, what would happen if you happen to touch the battery electrodes with wet, sweaty hands if our resistance was only 100 ohms? So assuming that our voltage is still 12 volts and our resistance is 100 ohms, if I do the same thing, current is equal to voltage over resistance. 12 divided by 100 is 0.12 amps. So we can see how dramatically the current has increased and the danger. That concludes this section. I will continue on in the next video and talk about power.